I've been using ASAP since 1988, and it plays a central role in almost everything that I do. Much of my work is straight light analysis, and ASAP is perhaps one of the most powerful tools that I know of for doing straight light calculations, finding straight light problems, and perhaps most importantly, identifying where the straight light is coming from. It's not enough to simply know what the straight light background is. You have to know where the problem is coming from and how can you correct it. And ASAP is essential for accomplishing those tasks. Now I'd like to show you how a straight light analysis is done in ASAP. We're going to show how ASAP is used to find straight light paths and identify those paths that are likely to be the largest straight light paths. And then we're going to show you how to do efficient calculations to get quantitative answers. In straight light, it's not enough to know what the paths are, you have to know how large they are, because most of the paths are entirely benign, much too small to worry about. We need to find those paths that have the largest power, and then find out how much power they have to see if we meet requirements. In ASAP, we can do this very, very efficiently, and we have the ability to find those paths and show them both graphically and in table format so we can find where our straight light problems are. We're going to be doing a sample straight light analysis of a relatively simple telescope called the Cassegrain telescope. In this analysis, we'll do it two ways. We'll first of all use the most straightforward approach, using the very simplest scatter models and the very simplest ideas about how we might do this straight light calculation. What we're going to find is that while this calculation is very simple, in practice it's not practical. We simply cannot get the calculation done in a reasonable time. We're then going to circle back. We're going to model the scatter properties in a more realistic way, showing how the Bsdf fitting utility in ASAP can be used to model not just simple BRDFs like Lambertian BRDFs, but can also be used to model very realistic BRDFs, and this can be done in a relatively straightforward way, even by beginning users. We're then going to show how ASAP's importance sampling or directed scatter capabilities allow us to get the calculation done very quickly. We now direct our attention over here to the plot on the right. This shows the system that we're going to be doing a straight light analysis for. This is called a Cassegrain telescope. It consists of a large mirror, sometimes called a primary, that it focuses light towards a smaller mirror, a smaller convex mirror called a secondary mirror, and then focuses this light on the detector. This is a very old design. It's been around for a couple of 100 years. But it's still used in many space telescopes, sometimes in a revised or modified form. And so while it's relatively old and simple, it's by no means outdated. Let's take a look at how we find this system in ASAP. We can go ahead and open up an editor. This particular system is defined in the file called cas.inr. In this system, I've entered the actual objects explicitly. That is to say, I've entered the objects by hand, putting in appropriate comments telling me which objects are which. This is possible for this system because it's relatively simple. Most modern systems we enter with CAD systems. That is to say, we have a CAD file which we import. This is much more realistic, but it takes longer. And so for the sake of brevity and simplicity, we're going to work with this relatively simple system. As we go down through here, we see one command for each object in the system. Near the very bottom of the file, we see a command called system2cas. This particular command in ASAP writes our optical geometry to a binary file that ASAP can read very, very quickly. This will be important to us later in our straight light analysis. After we've done our system2cas, we then trace some rays just to make sure that the optical system performs correctly. So for example, if we do an end telling ASAP that I'm all finished, I can go ahead and execute this file simply by clicking on the lightning bolt. ASAP comes down, it issues the command or sees the command $IO, which is a pause, telling ASAP to stop executing the file to allow me, the user, to enter some other commands. The command I'm going to enter is $IO, which says go ahead and pick up where you left off. ASAP then traces a series of rays through the system in the forward direction, showing me that the system is focusing correctly. Having verified the geometry in my system, as well as the fact that it focuses correctly, I can then proceed with my straight light analysis. The straight light path of interest, the path that I'm going to be looking at, is one in which light comes from outside the telescope, illuminates the interior of this baffle here, which we call the interconical baffle, We then scatter from that baffle to the detector. How should we do this? Well, we issue the end command, or we hit the end button telling ASAP I'm going to start again, and now going to create a file in ASAP to do this stray light analysis. In practice, doing stray light is typically done with scripts. Stray light analysis is complex enough that it's very difficult to do that in a GUI environment. So we'll begin here. The very first command I'm going to enter is system from cas. Recall that cas was the name of my binary file. It's the file that contains my system geometry and the optical properties. By saying system from cas, I'm reading that geometry into ASAP's memory so that I can work with it. I now want to add scatter properties to the object of interest. Here we go. The object of interest is called conbaff.inside, meaning conical baffle, interior surface. I merely issue the command object conbaff.inside, which tells me this is the object that I want to modify. I'm going to enter a very simple model. I'm going to assume that the scatter property is Lambertian, that is to say, the scatter characteristics, or BRDF, bidirectional reflectance distribution function, is constant as a function of incident and scatter angle. The easiest way to do that in ASAP is to enter the scatter command. Scatter random. I enter the diffuse reflectance, which for a diffuse black surface is typically around 5%, or 0.05, and I tell ASAP how many rays I'd like to scatter. That is to say, for every incident ray on the interior of the baffle, how many scattered rays shall I generate to actually propagate to the detector? For simplicity, I'm going to assume I'm going to scatter 10,000 rays. For every incident ray, I'll scatter 10,000 additional rays to the detector. At this point, I'm done. I can issue the command return, which says I'm all done with this object. I now need to define some rays that enter the telescope. We'll do this with the grid command. Grid elliptical, meaning it's an elliptical grid at the entrance to the telescope. The entrance to this telescope is located at the global coordinate z = -20. And I happen to know that the entrance aperture is a semi-diameter of 6. So it's 6 or -6 to 6 in the x direction, -6 to 6 in the y direction. And for simplicity, we'll simply use an in-plane grid of rays. We'll say 25 or one set of rays or one line of rays in the x direction and 25 rays in the y direction. For direction of the rays, I'm going to say source, direction. Directions in ASAP are entered as vectors. That is to say, we enter the x, y, and z components of a vector that is parallel to the direction of rays that we're going to trace. In this case, I'm going to be coming in at an angle of 20 degrees. 0 degrees in x, 20 degrees in y, and of course the z component will be the cosine of 20 degrees. Again, I'm all done. I would like to do a plot, so I'll say window, y, z, meaning the y-axis will be the vertical direction in my window, and the z-axis will be the horizontal direction. Profile says, give me a two-dimensional profile of my system, and I'm going to take one slice through the plane, or the depth coordinate, 0 to 0. I'm going to overlay that slice on top of my ray trace. So I'll say profile overlay trace plot. Let's go ahead and execute this file. We'll hit the lightning bolt. Here's our ray trace. We can see some of the rays have hit the conical baffle, and we can see many scattered rays coming off of this conical baffle, scattering into the hemisphere over that interior surface. Now we see our first problem. Even though we've asked for very many scattered rays, 10,000 scattered rays for every incident ray, none of those rays actually got to the detector. We're going to end up with no power whatsoever on our detector, in essence saying our stray light is 0, which is the wrong answer. We have two fundamental problems with what we've just done. First of all, we're wasting rays. We're trying to do a very difficult scatter problem in a brute force way and finding out that it just simply takes too many rays to get the answer. So we need a more efficient way of doing this calculation. The other problem with our analysis is that we're using a very simple BRDF model. We're assuming that the Lambertian model, or a constant BRDF, is appropriate, and this is almost never the case. So to correct this analysis and do it properly, we're going to have to do two things. We're going to have to make this calculation both more realistic and more efficient. We'll start by attacking the Bsdf problem and then move on to the difficulty and solution of getting enough scattered rays to the detector to get a correct answer. Let's begin. Let's take a look and ask ourselves what type of Bsdf or what type of scatter function is characteristic of black surfaces. This is measured data taken by Alan Ames of a black paint known as Aeroglaze Z306, a commonly used diffuse black paint used for aerospace applications. What we see here is Bsdf, or scattered light, as a function of scatter angle, where 0 degrees is perpendicular to the surface, or parallel to the surface normal, and 90 degrees is parallel to the surface. I'm showing two curves here, one for an angle of incidence of 0 degrees, and one for an angle of incidence of 80 degrees. At 0 degrees, the Bsdf is relatively constant. That is to say, the Lambertian model looks relatively realistic. We see a little bit of a rise on the left and on the right, but not very much. When we go to high angles of incidence, 80 degrees, the story is very, very different. We see that in the forward scatter direction, that is to say, rays are scattered along or near the direction of the reflected rays, or the specular direction, we find that the Bsdf gets very, very large. In fact, this is a logarithmic scale. So the Bsdf can be a factor of 10, 100, or even more higher than what it is at normal incidence. And to get the right answer for our Cassegrain telescope, we have to model this. This leads to an interesting problem. What sort of function could we possibly use that would model this Bsdf in a realistic way? In order to do that sort of modeling, we first of all have to define some variables. Here are three variables that we can use to describe both the specular direction, the direction of the incident light, and the scatter direction. These are called isotropic variables because they're characteristic of surfaces that have no intrinsic directionality to their surface, so-called isotropic surfaces. We start with the specular direction, or the reflected direction from the surface. We assume, or actually we use the convention, that the specular direction is in the YZ plane. If we adopt this convention, then we can characterize the specular direction by a single angle, theta naught, with respect to the surface normal. Our surface normal here is the z-axis, the surface itself being parallel to the x and y axes. The scatter direction, on the other hand, cannot be confined to the YZ plane. Rays can be scattered in any possible direction relative to the specular direction. This red arrow that we see here characterizes the scatter direction. We have an angle theta, or polar angle, but we also have an azimuth, and rather than using the azimuthal angle, we work in direction cosine space. That is to say, if we imagine an arrow pointing, or a unit vector pointing in the direction of the scattered light, the x and y components, or alpha and beta components, of that scattered direction are going to characterize the direction of the scattered light. Using this simple geometry, we then define three variables. We define the square of the direction, or square of the polar angle, sine squared theta, as our first variable. The square of the specular direction, sine squared theta naught, as our third variable, and then the product of beta and beta naught, that is to say the y components, as our third variable. When we have these variables, u, v, and w, we can then characterize any Bsdf that we wish in terms of a three-variable power series. This is done with the polynomial command. We express the logarithm of the Bsdf as the summation of powers of u, v, and w multiplied by coefficients. When we do this, we can then express any Bsdf in terms of the coefficients c, I, j, k. We may notice here that the variables u and w are represented in a symmetric way, and this is to preserve a property called reciprocity. Having done this, we can then represent our Bsdf of our surface. But to do that, we're going to use something called the Bsdf fitting utility. Let's take our measured data and fit it to find the coefficients. Let's do this by opening up a file within ASAP. We go over here to our ASAP file. Bsdf fit utility is the application that we're going to use, and we're looking for text files. I have here some text files which represent the measured data for the black surfaces that we saw before. Let's take a look at one of these text files before we first open it up. Here's the contents of a text file that contains BRDF data. The very first line is the angle of incidence in degrees, 5 degrees. Then comes our scatter direction relative to the direction of the reflected light. So this is minus 80 degrees. And then the BRDF data, minus 70 degrees, the BRDF at that angle, so on and so forth. All right, we're going to open up this file in our Bsdf fitting utility. Here it is. This shows our measured data in the forward and backward scatter directions. We'd like to fit this to a polynomial model, so we'll pick the polynomial tab. This is 5 degrees angle of incidence. We also want to bring in the 80 degrees angle of incidence data. So polynomial 80, bringing in, and we want to display them on the same graph, so we simply click on this multiple page button. So here's our 5 degree data, and here's our 80 degree data. We'll make the lines a little thicker so they're easier to see. Graph lines. And we'll zoom in. Well, we'd like to fit this data as well as we can within ASAP using our polynomial model. Let's go back. Our polynomial model has these powers of the variables u, v, and w, and we have to request a maximum order for the polynomial, n and m. We will try 2 because I happen to know that that works pretty well for this system. We say apply, and ASAP shows us all the possible coefficients with maximum orders n and m of 2. Now the fitting utility within ASAP can only fit 10 terms at a time. And so we're going to select the top 10 to start with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and lock the rest of them down. We go ahead and select Auto Fit. This represents our fit, which looks pretty good. We'll often find that several iterations give us some improvement. And this is actually looking very nice, but we'll go ahead and unlock the other coefficients as well and try doing just a little bit better. Auto fit. Okay, we've now fit our BRDF data. These are the values of the coefficients. Entering these into ASAP could be a rather tedious process. Fortunately, we don't have to do it. We can let ASAP do it. We simply go over here and say copy this particular model into ASAP. Click. Open up an ASAP editor and paste. Here's our BRDF model, already taken care of for us. All right. So now we have a more realistic representation of our BRDF data. We want to also bring in our geometry, so we'll say system from CAS. And it's always a good idea to put in some comments. Define BRDF model. All right, we're done with our fitting utility, so we can let that go away. Next step. We want to do our ray trace, but we want to do it much more efficiently. We don't want to race nearly as many rays. How do we tell ASAP where to send scattered rays? We're going to do this using the idea of importance sampling or important edges or directed scatter. Here's the idea. We have some surface from which we wish to scatter rays. We are going to define an edge, a little wireframe in space, if you will, and ASAP is going to be instructed to scatter rays only through that wireframe and no place else. In order for this to work, ASAP has to keep track of the proper power of the scattered rays, the BRDF function, the angles of incidence, angles of scatter, as well as the solid angle subtended by this edge. ASAP, in fact, does all of this automatically. The user need not worry about any of the numerics. The user only has to worry about placing the importance edge in the appropriate place. Let's go back to our geometry. All right. Here's the geometry we had before. We want to scatter rays from the interior of the interconical baffle to the detector. This is the detector back here. To do that, we have to define an edge. This edge is going to be entered here. Rectangle Z. What Z value shall I use? The detector, by placing the cursor on the detector and holding the shift key down, is at Z equal 10. And the semi-diameter of the detector is about 0.15 in both X and Y. We now have our edge. That's where we want to send our scattered rays. Define edge on detector. Okay. We want to generate scattered rays. How do we do that? We do that just the way we did before, but with the towards command rather than the scatter random command. That is to say, we're going to assign scatter properties. Object con baf.inside scatter model. Okay, we have a model up here. Let's give it the number 1. Scatter model 1. And then we say towards and tell it where we want to send the rays towards. This is the most recently defined edge in our system, and let's give it a number. The only thing that is important is that it not be a number that ASAP is already using. We'll assign a relatively high number to be sure that we don't overlap with anything else. 101. So towards edge number 101, and we'll say 10 rays. For every incident ray, we're going to generate 10 scattered rays going towards this particular edge. All done. Let's put our rays into our system. Define source. Grid elliptic Z, again, it's at Z equal minus 20. That's the entrance to our system. It's a semi-diameter of 6, so we're going from minus 6 to 6 in X, minus 6 to 6 in Y, 1 ray in the X direction, just for simplicity, and 25 in the Y. Source, direction, 0, sine 20, cosine 20. And do our ray trace. We'll do our profile command just as we did before. Here we go. We will close out what we did with ASAP before and execute the file. Now we see a very different story. Before we had 10,000 scattered rays, none of which made it to the detector. Now we have 30 scattered rays, 10 from each of the incident rays that we see on the interconical baffle, all of them making it to the detector. So our ray trace is much, much more efficient. ASAP is handling all of the numerical values so that we get the right number. To have a more realistic representation, let's put in a few more rays. We'll end what we had before, and we'll trace, maybe 501 by 501. Here comes our ray trace. Okay. Now the ray trace takes longer, of course, because we're tracing more rays, and the screen essentially goes black because we're tracing so many rays we're filling the entire screen. Not apparent in this is that a large amount of the time traced is being taken up by graphics. That is to say, the time required to trace or make pictures of all of these rays. We can speed up our ray trace substantially if we simply ask for fewer rays plotted while nevertheless tracing the same number of rays. In this example, we're not going to actually plot every ray. We want to plot, say, only every 100th ray so that the time required to trace the rays goes up quickly. Trace plot 100. That is to say, every 100th ray will actually be plotted, although we will actually trace every ray. Here we go. Here comes the ray trace. These are the rays scattered to the detector. And our ray trace is complete. And now we see the ray trace is done very efficiently. If we want to actually see the distribution of light on the detector, we have to ask for it. We tell ASAP that we're only interested in the light on the detector. Consider only detector. We want a window whose vertical axis is Y and horizontal axis is X. And we'll set up the resolution for our calculation. I'll say 15. Spots, position. This is the spot diagram of rays that are actually sitting on the detector. To actually get quantitative information, this command is actually writing that information to a file. We read that file with the display command and then issue the picture command. And this is the distribution of scatter or stray light on the detector itself. We see that the stray light distribution is not uniform, that in fact the amount of light on the bottom of the detector is brighter than the light at the top of the detector. We get numerical information by the color scale shown here, or we can ask for a cursor. As we move the cursor around, ASAP will print out the X and Y locations of the cursor, as well as the value of the stray light anywhere my cursor is located. Now let's make this a little more complicated. We've looked at only one stray light path, that is to say, scatter from the inner conical baffle. Let's now look at scatter from the mirror as well. To do that, we're going to have to do two things. We're first of all going to have to define a scatter model that's appropriate for mirrors, and secondly, we've got to tell ASAP where to send the scattered light that comes from the mirror. Let's go back to our picture of the geometry. We are now interested in scattered light from the primary. That is to say, we're going to scatter light from the mirror, reflect off the secondary mirror, and propagate to the detector. We want to use our idea of directed scatter or importance sampling to make this an efficient calculation as well as get the right answer. Where should we place our edge so as to get an efficient calculation? Well, one idea is simply to put an edge on the secondary mirror. For clearly, if we have to reflect from the secondary mirror after scattering from the primary, we have to go through the secondary mirror to get to the detector. But there's a better place to put the edge. If we were to sit on this mirror and look back into the secondary mirror, we would see within this secondary mirror, see reflected from this secondary mirror, an image of the detector. And this detector would be sitting back here behind the secondary mirror. So if we can find the image of this detector and its size, we can place an edge on that image, scatter towards that image, and get almost 100% efficiency of rays scattered towards our detector. How do we find where that image is? What we're going to do is we're going to use ASAP by tracing rays backwards from the detector to the secondary mirror. We're then going to stop on the secondary mirror and ask where that image is located. Here's how we accomplish that. I'll do an N to clear out our old geometry. We now have before us here our file that we're going to be using to do our backward ray trace. The file starts at the origin and then propagates from there to the secondary mirror and then stops. Let's do an N command and go ahead and run this file. Okay, so here's our rays propagating backwards from the detector to the secondary mirror and stopping. They're actually reflecting from the mirror, but they are not propagating any further because we've told ASAP to stop there. We want to find out what is the place of best focus. Where is the image located? To do that, we have to tell ASAP we're only interested in those rays that are on the secondary mirror. Consider only secondary. We then issue the command focus. Focus tells us to find the best focus for this rays. And ASAP says the best focus for these rays is at x equals 0, y equals 0, z equal minus 20. That's the location of our detector image. We now need to find out the size of that image. We're going to use the same idea, but we're going to use an extended source, not a point source. Instead of our grid, we'll use an emitting rectangle. We'll again place it on the detector, actually just slightly off of it. The size is the same. That is to say the detector dimensions are 0.15 by 0.15. Same thing. And we have to tell it how many rays to trace. We'll say 10,000. And we're going to confine those rays to a 20-degree angle just to make the ray trace more efficient. We issue the end command telling ASAP I'm done with my previous work, and go ahead and execute this file. Here's our backward ray trace. We know from our previous ray trace of a point source that the image of the detector is at z equal 20, so we say consider only secondary, move to z minus 20, that is to say take those rays that are currently on the secondary mirror and move them backwards along the trajectories to the image plane z minus 20. We then set up a window and do a spot diagram. This is our spot diagram for the calculation, and we see that the size of this window, looking down here, goes from minus 0.03 to about plus 0.03. That's the size of our image. That's the size of the important edge that we're going to use to actually direct scatter towards the image of the detector in the secondary mirror. Let's go back to our ray trace. All right, this is the file that we used to do our original scatter calculation. Now we're going to define another edge. We'll call it 102. Rectangle Z, we know the image is at minus 20. We know the dimensions are 0.03. So that's where we're going to send the scattered rays. Next, we have to define a new importance model. We don't really have time right now to talk about how to model scatter from mirrors, so I'm just going to enter a model that I know is appropriate. Model 2 will be called Harvey. And a typical mirror has parameters 0.1 and minus 1.8. Again, we haven't talked about what those parameters mean, but those are parameters that are appropriate for a mirror. Just as we assign scatter properties to the inside of the conical baffle, so we must assign scatter properties to the mirror. Object, primary, scatter, model, 2, towards, edge 102, 10 rays, and we're all done. We're ready to do our ray trace. End, run. Here's our ray trace. We can see that some of the light is indeed illuminating the primary mirror. When ASAP is finished tracing the parent rays, it generates the scattered rays from the primary mirror, which we see here. We're also going to be generating scattered rays from the inner conical baffle. Those are the same rays that we saw before. While ASAP is doing the ray trace, it's giving us information on the progress of the ray trace, telling us, for example, that it took 18 seconds to trace 320,000 rays out of a total of 475. This entire ray trace, which involved nearly 500,000 rays, was done in 30 seconds. Okay, we can now do exactly as we did before to calculate what the stray light irradiance is. Consider only detector, window yx, that's the size or dimensions or axes of our window. Pixel 15 is the resolution of our plot. Spot's position gives us our spot diagram and also calculates the stray light irradiance. The display command reads the file, and the picture command makes a picture of it. And so this is our stray light irradiance on the detector. Now this is our final answer, but for stray light calculations that's not enough. We need to know not only what is the stray light irradiance, but which contributors to the stray light irradiance are the larger of the two. Is it the inner conical baffle, or is it the primary mirror? When ASAP is doing the ray trace, it is keeping a partial history of that ray trace that includes most of the information about where the stray light is coming from. We can get access to that information by using the paths command. That is to say, we issue the command paths, and ASAP prints out a table. It's a numerical table that's relatively easy to import into a spreadsheet, but it tends to be just a little bit cryptic. Here's the basic idea. ASAP is telling me that for this stray light calculation, only 2 stray light paths were found. The objects that scattered the rays are given a number. It turns out that the very first object in my model was the primary mirror. The interconical baffle is the 17th object for my system. So we see here that one of the paths consists of rays that were scattered from the primary mirror, object number 1. Those rays are currently on object number 3, which is the number for the detector. They were previously on object 2, which is the secondary mirror, and they saw a total of 3 objects altogether. The total power of the stray light from these rays is 1.86 times 10 to the minus 8. This is how many rays in this scattered path actually exist, and this is the fraction or percentage of the rays out of the total stray light that this path represents. Similarly, path number 2 consists of all rays that were scattered from object 17. They're currently in object 3, the detector. They were previously in object 17, which is the interconical baffle, and they had a total of 2 objects hit altogether. This path consists of 99.98% of all of the possible stray light. So looking at this table, we see that it is scattered from the interconical baffle, which has over 99% of the stray light, which is the most important path, and that the primary mirror contributes only 0.02% of the total stray light. So if we have a stray light problem, it does no good whatsoever to correct the primary mirror. We have to direct our attention to the interconical baffle. Otherwise, the stray light will simply not be affected to any significant degree. Thus we see how ASAP is able to do efficient stray light calculations, do an accurate Bsdf fit to realistic Bsdf data, and how ASAP shows us not only the total stray light irradiance on the detector, but also ranks the stray light paths by importance and the total power that is on them, so that we can find out those paths that are most important and find out where the problems are so that we can solve them and improve our stray light calculation.